In this video, we learned to distinguish between so-called cis alkenes and trans alkenes. Cis and trans are related as so-called isomers, molecules that have the same molecular formula, such as C6H12, but have some sort of structural difference. In this case, with cis and trans, the structural difference is going to come down to the three-dimensional orientation of atoms within these types of alkene molecules. This topic is relevant for a variety of reasons, one of which is the term trans fat has come up a lot in the news in recent years, with trans fats largely getting a negative reputation in terms of their nutritional value. By the end of this video, we will be able to recognize what is referred to when one talks about a trans fat versus a cis fat. The spoiler alert here for this is trans versus cis fats are going to be dependent upon the three-dimensional shape of the alkene groups within the fat molecules. One way to compare and contrast alkanes with carbon-carbon single bonds to alkenes with at least one carbon-carbon double bond is to use molecular models. To compare and contrast these, we'll look first at our alkene molecule here. And in the alkene molecule, I've represented the different groups that are bonded to the alkene as these different colored spheres. The carbon atoms are both represented in black. So this is our alkene group right here in the carbon-carbon double bond. We'll notice here in this molecular model, it accurately shows geometry in that we have our trigonal planar shape. So if I lay my hand flat against the backside of this, the molecule relative to the alkene group lays flat against my hand, indicating this is a planar shape. And specifically, it's that trigonal planar shape with a 120-degree bond angle here, here, and here to spread the electron density as far apart as possible. In contrast, the alkane molecule with the carbon-carbon single bonds, you'll notice instead has a three-dimensional aspect to it, where if we look at the red atom is pointed toward you, the gray atom is pointed up, the purple atom, the purple group is pointed back toward me, and then this bond here lays in the plane of the screen or the plane of the page, showing us the tetrahedral shape where each of the bond angles is 109.5 degrees. Now, another key distinction between alkanes and alkenes comes in the carbon-carbon bond and its ability to rotate or lack thereof. In the case of an alkane, such as this, we can freely rotate around that carbon-carbon bond, and you'll see that the purple, red, and gray atoms or groups here rotate around freely relative to the carbon-carbon bond. We can do the same thing at the other end of the bond as well, and we can rotate around the green, blue, and yellow atoms, showing that this single bond here is capable of rotation. We could also rotate both groups at once, and this results in a variety of different shapes that the molecule as a whole can adopt. It's not locked into any particular three-dimensional shape. In contrast, the alkene is much more restricted. The pi bond here prevents free rotation of the carbon-carbon bond. So in other words, when I try to turn this bond or rotate it, it's very, very difficult. And in reality, that bond does not freely rotate. And so the blue atom here is always stuck opposite the green atom down here because there's no way to rotate around to make those appear on the same face of the molecule, meaning both pointed up or both pointed down, because of the fact that this double bond limits rotation. In definite contrast to the alkane, where we could have rotated around our carbon-carbon bond to put whatever group here on the right on the same face of the molecule, both pointing up or both pointing down, however we wanted by free rotation. In contrast, the alkene results in the groups being locked in place. And this fact that the groups are locked into place has important ramifications when it comes to the physical, chemical, and biological properties of these molecules. Due to the fact that those atoms are locked into place in the alkene molecule, we need terminology to describe exactly how the atoms are locked into place, because there are, in general, two possibilities of how the atoms could be locked into place around that bond that will not freely rotate. Those possibilities are that relative to the carbon-carbon double bond, which we see here, and I will put my carbon atoms in black, like they were in the video as black spheres. If we had groups attached here, I'm going to call those groups R, and I'm going to color them differently to indicate that each R group is different. And to further emphasize that, I'm not just going to call them all R, I'm going to call them R, R prime, to indicate that the red R and the green R prime are two different groups or two different atoms. I'll do a yellow group over here that I'll call R double prime to emphasize that it's different as well. And then finally, I will find some other color in my palette here to do an orange group coming down this way that I'll call R triple prime to indicate that these groups are different from one another. Now, one possibility is that looking at the structure, R in red and R triple prime in orange could be on opposite faces of the molecule. In other words, one of them is below the carbon atom that it's bonded to, and the other is above the carbon atom, higher than the carbon that it's bonded to. The other possibility is that instead, we could have a very, very, very similar structure where the only difference is the orientation of the groups around that double bond. So in other words, rather than having that R group in the upper right corner, what if we took these two groups and switched them and we put the green group pointed up and the red group pointed below? Let's go ahead and do that. So we could do R prime up here and then R down here. We could leave the atoms in the same positions on the other side of the molecule. So I'm just going to do my yellow R double prime oriented up as it was before, and then the last remaining piece was the orange group, which we called R triple prime, which I'm going to leave where it was before. So I left everything bonded to the carbon on the left exactly where it was locked into place previously, yellow, yellow, orange going down, and what we changed was the configuration of the R groups here and here. So green originally was down, now it's up, red was up, and now it's down. And now, in this case, if we were to sketch out a path from the red R group through the carbon-carbon double bond and to the orange R triple prime group, like we did over here, now we see that the path taken through the molecule, instead of being this zigzag like so, instead it's more like an upside-down bowl shape, where we could think of the bowl as being upside down right here through this pathway. So I've just drawn my makeshift bowl there in orange, and you can see how this forms kind of a tipped over upside down bowl when we trace the pathway through those different atoms. And what this is going to represent are two different isomers of the molecule, where one of those is described as cis and the other one is described as trans. This terminology is essential because of the fact that in these molecules that have a carbon-carbon double bond, we can't simply rotate around the bond to switch between the structure on the left and the structure on the right. Instead, those two structures would require some sort of chemical reaction to switch from one to the other. We can't simply rotate around a bond and do a simple process to convert the first one into the second one, or vice versa. Instead, it's a huge, great ordeal in order to interchange between the two. So generally, molecules that are cis remain cis throughout their lifespan. Molecules that are trans remain trans throughout their lifespan, due to the fact that we can't rotate around carbon-carbon double bonds. They're locked into place instead. And within this terminology, the way that we describe trans versus cis is we would refer to cis as the situation where the parent chain of the molecule from our IUPAC nomenclature, the parent chain forms this bowl type shape, the upside down bowl, or it could have been a right side up bowl, depending upon how the parent shape was, or it could have even been a bowl that was tipped to the left or tipped to the right. But the idea is it results from the two groups that are following the parent chain, the longest chain in the molecule, being both on the same face of the molecule. So both pointed down as they are here. They could have both been pointed up. They could have both been pointed left. They could have both been pointed right. They're making this bowl shape where the bowl can be in whatever orientation you want. We would describe this as cis. And that's cis relative to the parent chain. So what we're following here is we're assuming that the longest carbon chain follows this red and orange path of these R groups that we filled in here as generic filler groups to give this. On the other hand, trans is anything that is not that bowl shape. It instead is going to form a zigzag pattern. We're following the longest carbon chain. We have one group that's below the carbon it's bonded to. The other group of that longest carbon chain is above the carbon, or one's to the left, one's to the right. They're opposites, trans meaning opposite. So let's go ahead and try to apply this terminology towards some actual real-world alkenes rather than simply sticking with these generic kind of abstract R groups. Since the cis versus trans forms of an alkene have very different physical properties and interact with biological systems in very different ways, we need a streamlined, straightforward way to distinguish between the two forms. And we do that by incorporating the cis versus trans information into the IUPAC name of these molecules as one of the essential skills that we will learn. So let's take a look at an example problem here to illustrate how we would designate cis versus trans and how we would recognize cis versus trans within the structure of an alkene molecule. So we have this line angle formula for our alkene shown here. We will apply the standard rules for nomenclature that we previously learned, and if you need a refresher on those nomenclature rules for alkenes, look back at video number 312. Now, in naming alkenes, we always start from the end closer to the alkene group, even if there's a variety of other branches, and we number from that end closer to the alkene group to find the longest carbon chain that includes both carbons of the alkene. In the case of the molecule that we have here, that would mean we start numbering from this end and we go all the way through the molecule. Remember, finding the longest carbon chain means that it's the longest pathway through the molecule that we can trace out without having to backtrack or lift our pencil. Numbering from the end closer to where the alkene group is takes us like so. So we have 6 carbons in total in our longest carbon chain. So using our standard IUPAC terminology, that means that the parent name of this molecule is hexene, E-N-E, denoting that there is an alkene group. And the alkene group can be at different positions along this chain, and it's essential to mention where along that chain we find the alkene group. The alkene group is found starting at carbon number 2, and so we refer to this as 2-hexene. In some resources, you may also see this referred to as hex-2-ene, putting the number 2 immediately before the descriptor of the type of group, the alkene group that is at position 2. Either is totally acceptable for purposes of the class. The full name of this, without designating cis or trans, would be just 2-hexene, because the hexene encompasses all of the atoms of this molecule. There are no branches coming off of that, so we can go with just the name 2-hexene. But in order to be comprehensive in describing this molecule, if this could exist as both cis and trans forms, we need to specify which one it actually is. And remember, when talking about cis versus trans, the trans form was where the parent chain took the zigzag shape relative to the carbon-carbon double bond, and that could even be shown vertical like this. This would also be trans. There's a variety of ways to show it, but the crux of it is that relative to the carbon-carbon double bond, the 2 longest carbon chain directions, one goes in the opposite direction of the other. So here, one's to the right and one's to the left, going away from the carbon-carbon double bond carbons, with the structure over here on the left, one's going up and one's going down. Those all represent trans. In contrast, cis is shown by the bowl shape, where the bowl can be upside down, the bowl can be oriented to the right or the left, it can be oriented like a normal cereal bowl here that you could actually use. And in this case, what it will always be represented that relative to the carbon-carbon double bond carbons, both of the longest carbon chain groups are going to be in the same direction, both pointed toward the right, both pointed up, both pointed down, however you want to look at it. So we need to match what we see here to one of the templates down below in order to determine whether this is cis or trans. And it is indeed going to be trans. The reason being that relative to the carbon here on the right of our alkene group, the next atom of the longest carbon chain goes above that. Relative to the other carbon of the alkene group following the carbon chain, we go low, we go down, meaning these go off in opposite directions, and that would result in this being designated as trans. In order to refer to this within the name of a molecule, we simply plug that term at the very beginning of the name. So it'd be trans 2-hexene as the complete IUPAC name for this. And with alkenes, if it's possible for them to exist as both cis and trans, it is generally essential to indicate what the configuration of the molecule is, meaning designate whether it is cis or whether it's trans, since that feature dramatically impacts the properties of the molecule. As a follow-up to this, we should also be able to recognize the different cis versus trans isomers that exist of a molecule. And so one way that we could approach this is by asking to draw the other cis-trans isomer of the structure that we started off with and giving the IUPAC name for that. So we started with the trans isomer of the molecule, and so we need to draw the cis isomer. The way that I like to approach this is by drawing first the cis-trans component of the molecule. So to make sure that I draw it cis, I'm going to draw it like this upside down bowl. You could have drawn the bowl right side up as well, or shown it oriented toward the right or toward the left, or however you want to do it. But I draw that in first, and then connect to make the rest of the molecule with the carbon-carbon single bonds generally being shown as zigzags, just to represent the fact that they tend to stagger and be 109-degree bond angles. So we need in total 6 atoms in our chain. I'm going to number these 1, 2, 3, and I have made a mistake here because you'll notice that the carbon-carbon double bond starts at position 3 here. It started at position 2 in the structure up top. So I need to take a step back as I'm going through and be a little less sloppy about this. Instead, I need to erase what we have here so that now this becomes carbon number 1. Carbon number 2 is here, 3, 4, 5, and I add my 6th carbon to the chain at this end, because in order for it to be a cis-trans isomer, which is what we were asked to do, we are only allowed to change the geometry of the alkene group. We can't change the length of the chain. We can't change what carbon number the alkene group is at along that chain. It has to be at the same carbon number, but we change the cis to trans or trans to cis, whatever the case might be, to make this isomer. And so now that we have done this, we have still our total of 6 carbon chain, as we had in the highlighted structure at the top of the screen. And the only difference between these two structures is the orientation of the trans form being the zigzag and the cis form being this bowl shape. So this is going to represent our so-called cis isomer of the molecule. Giving the IUPAC name of that, one quick way to recognize cis-trans isomers is that the name will be identical with the exception of the designation of cis versus trans. So we can simply copy the name that we came up with before, which was trans 2-hexene, and just change that trans to cis, leaving everything else untouched. So it's going to be cis 2-hexene as the complete name for this isomer of trans 2-hexene. Now that we've got some of the fundamentals down of specifying cis versus trans isomers, let's take a look at a few real-world examples of some alkenes that are relevant to biology and relevant to nutrition, where the isomer property of cis versus trans is critical to the biological function of these molecules. Take a look at the top at vitamin A. We will see within the vitamin A chain, we have a few alkene groups here. We also have an alkene group within the ring here. We're going to ignore that. Those atoms are connected into a ring structure there where the carbons are all linked up and there's 6 carbons all connected together there. We're going to ignore that one and focus on these. Now, if we were assigning this as cis versus trans, in each of these 4 alkenes, we would need to specify each of them separately. And the longest carbon chain runs through the belt of the molecule right here. And so thinking about whether we would describe those as cis or trans, what we can see is that in each of the cases, if we look at the carbon atom on the right, we follow the longest carbon chain, it goes up above that carbon. If we look at the carbon on the left, in contrast, the longest carbon chain goes down relative to that. So we describe this bond as trans. We could do the same thing going all along here, where in each case, what we would find is that all of these would be shown as trans, where like here's the carbon atom, we're going down below that carbon to follow the longest carbon chain. On the other carbon, that's the other carbon of the alkene, we go up to get to the next carbon, the longest carbon chain, so we'd call that trans. And the same would be true if we went in and sketched that out for these 2 as well. So within the vitamin A molecule, which is required for proper function of the retina and is also essential for vision in low light, where deficiencies of vitamin A can result in poor night vision, this trans configuration throughout here is essential. And if any of those trans become cis, the molecule will no longer function as vitamin A. The biological function of it will totally change. So it's essential to be able to recognize this as trans. Beta-Carotene is a molecule that is abundant in carrots and other vegetables, particularly ones that have a rich, distinct orangish reddish color. And in the body, beta-carotene is useful because the body carries out a chemical reaction that allows beta-carotene, this giant molecule, to be cleaved and converted into vitamin A up here. Essentially, the beta-carotene molecule is split somewhere here down the center, and that results in the formation of 2 molecules of vitamin A through that chemical reaction that is carried out within the body. And in the case of beta-carotene, if we look also at its alkene groups throughout, what we will find here is that analogous to vitamin A, all of these alkenes, following this longest carbon chain through the molecule, we would note are all trans alkenes. And you should be able to recognize that those are all trans alkenes based on the information that we have learned so far. Lycopene, down at the bottom here, is a cool molecule that is found in tomatoes. It's found in a variety of other red fruits and vegetables as well. And it's responsible for the observed red color of tomatoes and others. So it's not an essential nutrient, but it does act as an antioxidant. And there have been some studies that have correlated lycopene with decreased incidences of cancer and other diseases. And the cis versus trans isomer of this is essential to its biological function as well. So looking at this structure, we see alkene groups scattered along this chain. There are several alkene groups. This pattern, by the way, where we see alternating double bond, single bond, double bond, single bond all the way through here is referred to as conjugation. And conjugation is actually what confers the bright red color on this, is the fact that we have this whole string of bonds here. And the way that those interact with light causes the molecule to be observed as a bright red color. And I'll give this one last group down here a highlight as well. Looking at the center piece of the molecule all the way from here through this entire conjugated region, every single one of these alkene groups we would describe as trans, because in every single case throughout the chain, if we follow the longest carbon chain relative to the one carbon, we come down following the chain. Relative to the other carbon of that same alkene group, we go up. So we follow that pattern down relative to the carbon of the alkene and up relative to that other carbon of that same alkene group. So that would allow these to all be described as trans. Now, what about the alkene groups here at the ends of the molecule here and here? Why didn't I include those in my earlier assessment of these being trans? Well, let's take a look at this. Using our definition of how to determine cis versus trans, we can look at the carbon atom on the right here for our alkene group. And if we were to specify whether the parent chain carbon goes up or down relative to that alkene carbon, we'd say it goes up. And then in order to determine whether this is cis or trans, we need to look at this other carbon, the carbon that I've circled here on the left. And following the longest carbon chain, we need to determine whether the chain goes up or down relative to that carbon. Now here's the problem. The problem is that for this particular structure, you have a methyl group going this way, 1 carbon, and a 1 carbon chain going this way. And so therefore, following the longest carbon chain through the molecule as we do for IUPAC nomenclature could take you up or it could take you down. And it doesn't matter which of those routes you choose in coming up with the IUPAC name, you're going to end up with the same name and the same structure regardless. And so as a result, there is no cis-trans geometry at this position. And the reason is that those two groups, the two methyl groups that are bonded to the same carbon, are completely undistinguishable. And so therefore, it doesn't matter which one goes up and which one goes down, since they are completely the same. So there's no cis-trans geometry. It is irrelevant. And the same is true here at the right hand of the molecule, because taking a look at our carbon right here, the longest carbon chain could go this way because that's 1 carbon, or it could come this way because that's 1 carbon as well. So with that being a tie, there's no way to distinguish what's the actual longest carbon chain here. They're identical. So in other words, these two groups could switch methyl group for methyl group and you'd have exactly the same molecule, indicating that there is at this end of the molecule no distinction between cis and trans geometry. So don't try to classify that group as cis versus trans. So the general rule here is if you have two identical groups bonded to the same carbon atom, then cis and trans can't exist. That would be the case also if you had a structure where the alkene group is at the very end of the molecule, so there's just hydrogen atoms here on this carbon. It doesn't matter what is going on here and here, since this has two identical groups bonded to the same carbon, two hydrogens there can be no cis or trans for this entire alkene group, because you'd have to have two different groups there in order to be able to recognize whether following the chain you would go up or down to get to the next carbon in that chain.